Welcome to this explainer. Today we're going to dive into a tiny, easily missed detail you've probably stared at on a flight but never truly understood. You know the one, you finally snag that window seat, you lean your head against the glass, and right at the bottom there's this little hole. Honestly, if you're not expecting it, it can cause a brief flash of panic. But I promise you, it's completely normal, and it actually holds an incredible engineering secret.
I mean, it looks exactly like a manufacturing defect, doesn't it? Why on earth would engineers deliberately drill a hole to weaken a window? We're talking about a machine flying at 35,000 feet where a single crack could literally be catastrophic. It feels like something that just slipped past quality control on a jet that costs more than most people's houses. But, as we're going to see, it isn't a mistake at all. That little hole is actually one of the most carefully calculated safety features on the entire aircraft.
Okay, let's dive into how this actually works. To solve the mystery, we first need to look at how the window is built. It's not just one thick piece of glass. It's actually three distinct layers, stacked together like a sandwich. You've got an inner pane, a middle pane, and an outer pane. And notice exactly where that tiny hole is placed. It doesn't pierce the inner layer facing you, and it doesn't touch the outer layer facing the sky. It only goes right through that middle pane.
So, why this whole three-layered setup? Well, it all starts with a problem most of us never even think about while we're up there sipping ginger ale. At cruising altitude, around 35,000 feet, the outside air is brutally thin. If you were suddenly exposed to it, you'd pass out in seconds, because the pressure out there is just a tiny fraction of what we feel on the ground. Meanwhile, inside the cabin, engineers are pumping in thick, comfortable air, pressurizing it to simulate an altitude of about 6,000 to 8,000 feet.
And that creates a massive physical gap. The thick air inside the plane is pushing outward, and I mean pushing incredibly hard, against every single surface of the fuselage. It's essentially like a giant balloon under constant, unyielding tension for the entire duration of the flight. And your windows? They have to hold all of that outward force back.
This tension introduces a hidden, quiet danger known as cyclic fatigue. You see, materials like metal and glass don't usually fail the very first time they're put under stress. They fail after being stressed and released in the exact same spot thousands of times. It's sort of like bending a paperclip back and forth until it snaps. Every single time a plane takes off, the cabin pressurizes. During cruise, it holds that immense strain, and when it lands, it depressurizes. That's one full cycle. Commercial jets do this thousands of times over their lifespan, and cycle after cycle quietly weakens materials in ways you can't see with the naked eye.
Now here is where it gets critical. Anytime you cut an opening into the metal skin of a plane, like a window, it instantly becomes a massive stress concentration point. If you were to use a square window, the force of all that pressure doesn't just spread out evenly, it piles up. Those sharp 90-degree corners give that repeated cyclic stress nowhere to go but straight into the surrounding material, literally tearing it apart at the microscopic level over time.
And sadly, this isn't just a theoretical problem. It's a hard lesson learned in blood. Back in the early 1950s, a pioneering passenger jet called the Havilland Comet suffered a string of catastrophic in-flight breakups. When investigators painstakingly put the wreckage back together, they found a devastating flaw. Fatigue cracks had started right at the corners of the aircraft's rectangular windows. That exact tragedy fundamentally changed aviation engineering forever.
Engineers quickly realized they had to change the geometry entirely. That is exactly why today, every airplane window you see is perfectly rounded. By completely removing the sharp corners, the physical force flows smoothly around the curved edges. The stress doesn't pile up in one dangerous spot, it just glides around the opening. But, as we'll see in a second, fixing the shape alone just wasn't enough to guarantee the windows would survive decades of pressurization cycles.
And that brings us right back to our three panes. Let's take a look at the innermost pane, the one closest to you. This inner pane, it isn't structural at all. Its one and only job is to be a sacrificial shield. It protects the incredibly important structural glass behind it from your scratched rings, bumped luggage, and spilled coffee. It just takes the everyday wear and tear of a cabin full of people. But now consider the gap between the middle pane and the outer pane. If that middle pane were completely solid, with zero holes, we'd have a very serious problem on our hands. The air trapped in that little gap would heat up and expand, building up its own totally mismatched pressure against the glass. That trapped air would put intense cyclic stress directly onto the middle layer, a layer that really isn't meant to do the heavy lifting of holding back the sky. Over years of flights, this unmanaged stress could actually cause that middle pane to crack from fatigue.
So let's look at the brilliant solution. That tiny, seemingly random hole is called a breather hole. It allows a steady flow of air to pass between the cabin and that middle gap, equalizing the pressure perfectly. Because the pressure on both sides of the middle pane is now exactly the same, the middle pane is completely removed from the structural fight. It's essentially just floating in perfect equilibrium, returning to a calm, unfatigued state and resting comfortably at cabin pressure. Because of this equalized pressure, nearly 100% of the actual job of holding back that incredibly thin 35,000-foot sky falls directly on the outermost pane. The outer pane is a thick, specially engineered piece of structural material built specifically to take the full brunt of the pressure differential entirely on its own.
But what if the absolute worst happens? In the extremely rare event that a piece of debris strikes the plane and the outer pane actually cracks, suddenly the pressurized cabin air tries to rush out. Well, this is exactly when the middle pane activates. Remember, it has been resting completely unfatigued in reserve for years, all thanks to that tiny breather hole. Instantly, the pressure hits it, and because it is totally unfatigued, it is more than strong enough to take over the load, holding the pressure long enough for the pilots to safely descend.
This right here reveals a profound philosophy found in serious safety engineering. Never, ever rely on just one component to work perfectly forever. Always build an overlapping backup. But here's the real secret sauce. That backup system must be kept totally free from the daily stress that wears down the primary system. If both panes were fighting the pressure every single day, they'd both be fatiguing at the exact same rate. The whole ensures the backup stays fresh.
And we actually see this exact same philosophy of managing and compartmentalizing chaos in entirely different fields. Think about emergency response networks. When disaster strikes, you have highly distressed, panicked callers flooding the 911 system with raw, chaotic input. If there was only one person handling the calls, coordinating the logistics, and driving the ambulance, the entire system would instantly collapse under the stress.
To survive this, the primary operator doesn't just absorb all the panic. They filter it. They act exactly like our tiny breather hole. They route the chaotic information through layered, overlapping backup systems, separating location, priority, and instructions to create a highly organized, safe, and deliberate response out to the fire trucks and police. It's all about ensuring the raw stress doesn't overwhelm the critical structural response.
Back on the airplane, that three-pane window with its tiny breather hole is just one single layer in a vast, invisible network of quiet, overlapping backup systems. The aircraft is literally filled with them. There are pressure warning systems that alert pilots long before humans even feel a change. There are oxygen masks sitting in the ceiling ready to drop automatically. There are scheduled structural inspections strictly designed to catch fatigue early. Each system is designed to gracefully catch what the others might miss.
Now at this point, you might be wondering, why do we even have a pressure differential in the first place? Why not just pressurize the cabin perfectly to sea level and avoid this entire cyclic fatigue headache altogether? Well, it all comes down to a massive engineering trade-off. To build a metal fuselage strong enough to hold sea level pressure up at 35,000 feet, the plane would have to be incredibly thick and heavy. It would burn absurd amounts of fuel, carry fewer people, and your tickets would be astronomically expensive. The pressure differential is the necessary compromise that makes modern air travel possible.
And that tiny hole is the ultimate symbol of that compromise. It is a brilliant, quiet solution refined over decades of hard aviation lessons. So the next time you're sitting by the window gazing out at the clouds passing far below, take a second to look down for that tiny dot of negative space. It's absolutely not a flaw. It's a calculated, life-saving decision. And as you trace its edges, ask yourself what other invisible, brilliantly designed backup systems are quietly resting in reserve, holding back the chaos of the world right now.